Everyone got quiet a minute early, so let's start early. Good afternoon. Welcome to the Best Tutorial Track for ITSEC 2021. This track has the 3 tutorials that the tutorial board selected as candidates for the Best Tutorial Award, which will be presented Thursday night at the banquet. I'm Lee Lacey. I work for SoarTech here in Orlando, Florida. I'm the session chair, and my co-chair is Rob Lechner from Boeing St. Louis in the back. Hopefully you've downloaded the ITSEC app by now. There's a way to go through there to fill out surveys. We would appreciate your feedback because we can improve the conference year over year if we have that information from you. Our next tutorial is 21032, Addressing the Challenges of Rigorous Simulation Validation. We're fortunate today to have the world's 2 leading experts on VV&A to present the tutorial, Simone Youngblood and Dr. Michael Petty. Simone Youngblood is a member of the Johns Hopkins Applied Physics Laboratories. She's principal professional staff there. She has an extensive background in simulation development and credibility assessment. She's served as the DoD VV&A focal point for the past 25 years. She was the editor of the DoD VV&A Recommended Practices Guide, which is the document to help you in this area. And she's chaired the development of several VV&A related standards, including IEEE Standard 1278.4, 1516.4, and MIL Standard 3022. Ms. Youngblood has served as the VV&A and/or accreditation agent for numerous M&S efforts that span a broad organizational spectrum to include PEO IWS-1, DTRA, the Domestic Nuclear Detection Office, the U.S. Naval Air Systems Command, and U.S. Army Medical Research and Material Command. She has a BA in mathematics as well as a BS and MS degrees in computer science. Her co-presenter, Dr. Michael Petty, is senior scientist for modeling and simulation at the University of Alabama in Huntsville's Information Technology and Systems Center and an associate professor of computer science. He served as the director of UAH's Center for Modeling, Simulation, and Analysis for 10 years. Prior to joining UAH, he was chief scientist at Old Dominion University's Virginia Modeling, Analysis, and Simulation Center, VMASC, and assistant director at the University of Central Florida's Institute for Simulation and Training, IST. He received a PhD in computer science from the University of Central Florida in 1997, Go Knights. Dr. Petty has worked in modeling and simulation research and development since 1990 in areas that include verification and validation methods, simulation interoperability and composability, human behavior modeling, multi-resolution simulation, cybersecurity modeling, and simulation software frameworks. He has published over 240 research articles, chapters, and papers, and has been awarded over $17 million in research funding. He served on National Research Council and National Science Foundation committees on modeling and simulation, is a certified modeling and simulation professional, CMSP, and for 5 years was editor-in-chief of the scholarly journal Simulation, Transactions of the Society for Modeling and Simulation International. Please join me in welcoming Simone and Michael.
So can everyone hear me? Awesome. Can I just say it's so good to be here? Just so awesome. I'm thrilled. Thank you for joining us for our paper on addressing the challenges of rigorous model validation. Now, what do we mean by rigorous? We're going to get into that. We talk a lot about modeling, the verification, the validation, and what we want you to get from this particular session is, how do we distinguish between these concepts of verification and validation? When we talk about validation and rigorous validation, what role does the referent play in that process? And we're going to be talking definitions here soon. And, what are the various approaches that you can use or employ to develop a rich referent that can support your validation effort and support that idea of that robust validation process. And then, what constitutes rigorous validation? What do we mean when we say that? What's different when we say validation and rigorous validation? What does that, descriptor mean? And then how do we match those validation methods to your available reference? So your referent, the thing you're going to compare to, the information you compare to, is going to dictate what kinds of processes you can employ. The availability, the breadth and depth of that information. So that's what we want you to take from this class, be able to address those particular issues. So we're going to get into motivations and as I say, definitions here, because we want to be all talking the same language, if you will. And then we are going to talk about validation uncertainty and risk and how that comes into play. And then verification and validation methods. Then we're going to get into this referent issue that I talked about because it is so key and central to the validation process. And then Michael's going to talk to you a bit about various validation methods for, single validation metrics, things like firm track range, versus time series data. So what if you're looking at flight, a system flying, a fly out? Then you have to assess across a set of points. You have to validate across a set of points. So we're going to talk about that, and then we'll get into some conclusions and recommendations. So why are we concerned about this issue of validation? And in particular, again, this descriptor of rigorous validation. Well, you can start to see the seedlings for this in some memos that came out of the Director of Operational Test and Evaluation office. At the time, the director was Dr. Gilmore, and he had some specific concerns when we're using simulation in support of test and evaluation. So if you've participated in other lectures or in other tutorials, you will have seen that there's a breadth and expanse over which M&S is applied, modeling and simulation is applied. But it has a real firm rooting in the test and evaluation community now. That wasn't always so, but we are dependent on it for test and evaluation. We can't test where we want to the extent that we want to. And so what we want to do is use simulation to help us understand some of these areas where we may have some of that uncertainty. So Dr. Gilmore put together a couple of memos. His first focused on this issue of M&S in support of T&E, and he raised this issue about the need to have credible constructs, credible validation methods employed, heavily dependent on statistical methods. And again, we're going to talk about that later. And then he came out with a reiteration and a clarification of his original memo, again, reinforcing this idea that we need to apply these rigorous validation methods. From that, I know IDA, in support of DOT&E, put out a handbook on statistical methods that can be used in validation. But there is just this concentration, this desire to really focus on how we're doing validation and how we're applying the correct kinds of methods in the correct situations, again, given the kind of referent data that you have available. So we've done this tutorial before, and sometimes we get our responses back and people say, well, you spend a lot of time talking about definitions at the beginning. And that's purposeful. We do that because we need to set the context here. And we need to, like I said, have that common language. So we start, at the beginning here with the definition of model. So we're all cognizant of models, model aircraft, model trains. There's mathematical models. But what we're trying to get at is some representation of a system or something that we're trying to capture, the logical construct of its performance, it's the phenomena associated with how it works, et cetera. Simulation now. We are now looking at not only the thing itself, but how it operates over time, how it performs over time, and how it's affected or stimulated even by things like the natural environment, by other platforms, other systems where you might have interactions happening across those systems. So simulation, we're really trying to emphasize that concept of representation and performance, right, and effectiveness. So you can sort of start to see that tie to the test and evaluation community, where you're looking at system performance and system effectiveness, right? So now we have two terms which most people aren't as familiar with as they are with model and simulation, and that's the simulant and the referent. So the simulant is the thing that we are trying to represent with our model and or our simulation, right? So it's the object, the phenomena, the thing that we're concentrated on. And the referent is our best knowledge, the body of knowledge that we have about that thing, right? About that system that we're trying to represent. So, again, this is why the referent becomes so important, because it helps us to get some insight onto how the system should perform, right? Right? So the referent is a key player here. Now, when we say referent, where do we derive that referent from if it's such a key and important construct? Where does it come from? Well, it can come from the empirical data, and that is, I'm going to talk about two different pieces here. You can get information from the actual operational environment. We tend to focus on like the test and evaluation, the live tests. But you can also get information from the operational environment. And I'm going to say the one thing I will say about VV&A, the sort of a mantra that I have, is that, it's not a one-stop shop. I mean, it's not a single point in time where you do VV&A. VV&A is an evolutionary construct. I always say we play the long game. We're building information over time. So with our referent, that's something we have to consider as we're building our referent. What are the different opportunities, the different sources? With the test and evaluation community, you might start with ground test, land-based test, and then you might evolve to your live test data. And then over time, after you've filled your system, you may be able to leverage information coming out of the operational environment, feeding that back in, and growing your knowledge about how the system operates, how it's affected, and then feed that into your simulation. And I'll talk about a good example of that another time. So you have operational data in the real world, and then of course you have your test and evaluation data, your live test, like I said, your ground-based test, any kind of test where you're assessing system performance and you're, again, feeding that back in. Could be theoretical. I mean, NASA, they do a lot of missions into places where we've never been. They send out their scouts to garner some insight. But a lot of the information about performance, system performance, of the orbiters, of the lander modules, lunar, that comes from theoretical assessment, hypothesis based on knowledge of the laws of physics, et cetera. So, there may be some theoretical data that can be derived and calculated to provide you some understanding of how the system is expected to perform. Then there's simulation data. Now, in this case, what we're talking about is we're comparing two simulations against each other. And there is a community where this happens all the time. And you start to see it here in Florida at the time hurricane season starts, right? You have multiple models, European model, the GSF model, different models created to understand how you're going to develop a weather forecast. What are the different phenomenology that is occurring out there that will impact the weather potentially. And so they use these different models, which are built differently. They have different levels of fidelity. They have different tempos as far as how often they're fed data, the currency of the input data that they receive. And so they're all different, and when they compare them, what are they looking for? They're looking for trends. So if you see a hurricane forecast or you see a snowstorm up in the East Coast, we see this all the time, and you have the meteorologists there, when they start to see the trends in the data, they start to get very confident in their forecast. When those models all diverge, then you start to see them saying, well, we're not quite sure what's going to happen. So this idea of trending, of registration, the Missile Defense Agency uses the concept of registration a good deal. So they have different models, like a design-based model, a spec-based model, and then a model on the right side of the V, if you will, the systems engineering V. And they compare the two models to see the trends. And so when we talk about a reference source, that idea of trending data, comparing two simulations, that doesn't say one is right and one is wrong. It just means that we start to see if two different models come with two different approaches and they're compared, that there is some consistency in results. And then the one referent we're probably most familiar with is our subject matter experts. And I'm a big believer in the use of subject matter experts. Their inherent knowledge, their study of the field is very important. But as you would expect, based on the names, their information, their insight is subjective by nature. They have their own ideas of how things work. And I've seen this in validation tests where I'll have 3 different subject matter experts come up and give me 3 different opinions on what the right answer should be, the correct answer should be. So we'll talk a little bit about that in a few minutes here. And then, of course, as I said, you want to use all the information you can, all the referent data you can, to build that, a really robust set of knowledge, right? So you can combine this set of reference to, create an even stronger one. So referent, key piece. The other is intended use. I can't tell you how many times people come to me and say, is the model valid? And I'll ask them, valid for what, right? So the idea here is that you're building a model and that you're assessing it, but you're assessing it for a specific purpose, right? And that entails, specific metrics of interest. You want the model to produce certain values, metrics, that are going to be used to support decisions, right? So probability of detection, probability of false alarm, there are all kinds of metrics that you might be interested in. So this idea of intended use is central to the concepts of verification, validation, and accreditation, but particularly that idea of validation, which we're going to get to in a minute here. So another thing I see happen a lot is the conflation of the concepts of verification and validation. And to me, they're very specific things. Verification is very requirements-driven, right? So when you build a system, systems engineering, you have a specification, a requirements specification, and you verify that you've met that specification. Very similarly, when you build a model or simulation and you're using it in support of intended use, you have a set of requirements for that use. What kind of capability needs to be in that model? What level of fidelity? What kinds of interactions? What metrics does it need to produce? Or at least, feeder metrics that will be used in the post-processing to produce the metrics of interest. What kind of infrastructure or architecture are you using? Is it a distributed simulation? Are you talking high-level architecture? Are you talking TINA? What are you looking at as far as the construct of the simulation? What are the timing issues? What are the coordinate system issues, right? I can tell you in distributed simulation, that's always a killer, right? So, we're really looking at the structural integrity of the model or simulation when we talk about verification. And, ensuring that all the things that we need to be able to represent the systems of interest reside in that model at the level needed for the intended use. Validation, on the other hand, is now focused solely on representation. Now I have built this virtual world. It operates as expected. It's stable. It doesn't, you're not getting crash errors all the time. And now I'm looking at, well, how confident am I in those representations, right? And so, again, you see here in this definition that you're talking about the model or simulation and its associated data, so the input data is key to this, whether or not it's an accurate representation of the real world, so that comes in the referent, that's the referent that we're talking about here, from the perspective of the intended use. So that tells me if I have to, if I'm looking at a tank representation, a simulation of a tank, do I need, for my intended use, for the turret to move and the treads to move? Is that important to me? Or is it simply that I need to know the location of the tank and the direction it's heading, right? So my intended use is going to tell me that, and it's going to help dictate the level of representation that I need. And then I'm going to have to go back to developing my referent so that I have information at that level, or try to get information at that level to do the assessment. So, a lot of times when people talk about models and simulations, there's almost the impression that, it's a direct copy of the thing that's being represented. And I can tell you, having worked in this arena for many, many years, that's not the case. You're usually talking about an abstraction of the simulation. And so there's going to be uncertainty associated with that. And uncertainty plays in two different ways. It plays in terms of aleatory, which is uncertainty relative to variability in the model, and epistemic, which is uncertainty in our knowledge base and our referent that we talked about. So what we're looking at here is a picture that was developed by Dr. Dale Pace, where he really tries to tease out, what are some of the sources of that uncertainty that we're dealing with. And so if you see going down the left to the bottom here and into the inputs, you're really seeing that aleatory type of uncertainty that's driving you. It deals with the variability in the simulation. And then when you go to the right side there and you're talking the referent, that again, it's knowledge, it's what we know, and there will be uncertainty there. So one of the key challenges in sort of the art in verification and validation, and particularly in validation, is helping to frame what where we have uncertainty in the referent and understanding the impact of that. Are you going to have uncertainty? Absolutely, you're going to have uncertainty. How much uncertainty is an open question? That's what we need to look for. And then, what's the impact of that uncertainty is also very important. But along with that is the selection of the measure, or the techniques, the methods that we use to help manage some of that uncertainty, right? And we'll get into that as we go forward. So I'm sure many of you have looked at the concept of type 1, type 2 errors, right? Type 3, probably not as much. You've probably heard about the type 1 and type 2. So when we're talking about this concept of validation, we want to make sure we're using the simulation in the best way possible, right? We want to have as much confidence as we can have, And this table here shows you that, how you use the model and when you use the model, whether or not that model is considered valid, again, for the intended use, there is an impact, and that ties into this concept of type 1 and type 2 error. So if I have a valid model, but I choose in my accreditation I don't believe it, maybe because my validation evidence isn't convincing enough to me, then I might choose not to use the model, and then I would incur a type 1 error where the model could have very well been used, the simulation could very well have been used to answer the question, but it was not. And there's a great example of this. And I don't know, Michael, if you're going to talk about the crater model. I don't think we are talking about it this time. No, it was in his previous, in the previous version of this tutorial. He did talk about that, but it was an example where the referent, the size of the referent. So this was a model of what happened in the space shuttle when the foam hit the leading edge of the wing. And the model had been validated, but it had validated to a much smaller size particle hitting the wing. And so when they had the accident with Columbia, they employed the model, or they looked at employing the model. People said, use the model. And they said, well, we don't believe the model because we don't think it's validated or valid in the situation. Well, it turns out it was. It turns out it did predict that there would be a hole as a result of the foam hitting the leading edge of the wing. So this is where you had a type 1 error, and in this case, it was not a less serious error. But in most cases that we work with in the DoD, it would be considered a less serious error than misapplying on the top here, in the top middle, a simulation that's not valid and using it as the basis for decisions, key decisions relative to system viability, design decisions, et cetera. And then you have another case here where the model's really not relevant. And I've had this where you encounter a situation where the sponsor is very tied to a model, but it might not be the best model, or it might actually not be a model that's really suited for the kinds of study that you're looking at applying it for. So, when we make our selections of models, it's very important to be framed, and that's why we spend so much time providing context at the beginning. It's very important to understand what is my intended use, what is my referent? Am I able to create a reference sufficient to validate my simulation? And, what remaining uncertainty do I have? And based on that uncertainty, should I be using this simulation for my particular application? What kind of error might I encounter if I am? So this takes us to the VV&A process, right? So VV&A, verification and validation, to me is all about producing evidence. I'm building my case for confidence. Starts with my verification case, which is all about structural integrity. I have everything that I need to, be confident that the simulation works. It has the correct, it has the appropriate representation. And then I have to go in and I have to do the evaluation. So you see the terms that we've been talking about here. You have requirements at the top. You have your simulant to the right. I think is this a pointer? No, I don't see it working. Oh, there it is. Okay, so you have your requirements, right? That drives the development of your simulation, right? So we always talk about conceptual model, and Phil's in the audience. She knows my true devotion to the concept of a conceptual model. But the conceptual model is the understanding of how the world that you want to simulate is supposed to work. It's the concept of that, right? From that, and so you're going to, here's what I need, here's what I want to build. I'm going to verify that I've captured everything in that conceptual model. Then I'm going to build an executable model from that concept. It may be a design, it may be a more abstract conceptual model. I'm going to build an executable model, and I have to verify back to the conceptual model. At the conceptual model stage, if you really are abstract, you can also do some level of validation against the simulant, right? Our knowledge of the system being represented to ensure I've captured everything I need. Then I build that executable model, I verify, and then I'm going to produce results. We talked about validation metrics. I'm going to produce results, and I'm going to compare those back against my knowledge about the system being developed, right, being represented. So, the black arrows are those transformational pieces where your model morphs into, the latter stages of development until you have results. And then these dotted lines are those comparisons that we talked about, those verification and validation, is building your evidence set. Now, we're not going to spend a lot of time on verification in this particular lecture. It is the focus is validation. But that being said, Lee mentioned the recommended practices guide that was developed under what is now the modeling and simulation enterprise, right? Thank you. Which was DIMSO at the time we were working. Phil and I were working there. But there is a section on techniques, V&V techniques, and it talks a lot about primarily verification techniques that can be applied. So, when we, focus on this concept of verification, and if you are in a situation where you have to address the concept of verification, I encourage you to go through this great resource here that was developed by Dr. Osman Balchi. And it'll give you insight into the various techniques that can be applied and, how you might select the best for your particular situation. So with that, we go from verification, we're moving now into the validation world. And we need to start with this idea of referent. I talked to you a little bit about, the reference sources. But really, what makes a good referent? It says ideal referent. We live, being a V&V person, we live in the world of optimism, right? We can build all the information we want and produce an ideal referent. But the fact is, it's a long and arduous journey to get to the referent, right? But what you're trying to do is understand performance envelope, really, is what I like to think of. It's an envelope of what you're trying to get at here. So with your validation, it's not a one-dimensional, two-dimensional concept. It's multi-dimensional. And so we are looking at, how far can I extend? What are the threat representations I'm interested in? If I can't get to the one, maybe it's a future system, so I can't get there. What is something that's close? Am I extrapolating too much? And this is a problem we encounter. We're able to build our referent so that we have some knowledge, but it doesn't overlay. And Michael has a very good slide for this later on. It doesn't totally cover the space that we're interested in. So how big is that space? How far am I extrapolating? What we really like to do is draw out our knowledge and use our simulation to help dictate where we test so that we can draw out our knowledge to the areas where performance starts to edge off, right, at the boundaries, because that's where you're learning the most, right? So, being able to, and we'll talk about this in a minute, really connect with your testers to help drive the information as far as possible out so that you're interpolating between known points versus extrapolating beyond our knowledge. Because what's happening when we're extrapolating? We're interjecting that uncertainty, right? And trust me, there are a lot of times where there's just no getting around it. But that is something we have to live with. So we're going to draw our observations from the simulant. Of course, this is a simulation of like a live test. It's a simulation. It's not actually operational environment. So there are issues that you're going to have to deal with. You might have measurement errors that you encounter that calls into the question the viability of the referent data that you have. So a lot of times when people say, oh, I'm going to compare my simulation results to my referent data, if something doesn't look right, people immediately point to the model or simulation. Sometimes it's not the model or simulation. Sometimes it is your referent data that you have a problem with. It's measurement error and things like that. But you do want to draw your information from authoritative data. And when you live in the test world, that means that you are using test data that's gone through a review, just because of issues like measurement data that I talk about. So I'm always in a situation in working on the V&V where I have to produce a schedule. Folks want schedules. And, I always say, when is my simulation delivered to me and it's working? And when do I get my referent data? So people say, oh, well, the test occurs in November. So you'll get your test data in November. I'm like, no, I'm not getting my test data in November. I'll probably get it in January, because there's a process by which the data is drawn, it's captured, it's reviewed, and then a report is developed and it's sent out. So in developing that schedule, you have to be aware that you're not going to, in most cases, again, I live in the world of optimism, but still, you're not going to turn around the next day and get your test data. There's going to be a gap. And sometimes it's a significant gap. I just encountered that with a program I was working on. Okay, so, and then, again, as we're building this reference, we are looking for, what are the known areas of uncertainty, right? What are the things that drive up our uncertainty with the referent? So as we're producing it, as we're capturing the information and the insight, how do we account for all of these particular issues? Do we capture information and insights on those? Okay, so what are the challenges associated with developing that ideal referent there? Okay, the ill-defined intended use. If, there's a poem, it's Robert Frost, if I don't know where I'm going, any path will do. And I encounter that a lot. You're just saying, oh, build me a referent. A referent of what? I need to understand what it is we're focused on. And primarily there, it's the metrics of interest. Now, when you're in the test and evaluation world, again, you have an integrated evaluation framework, which talks to those metrics of concern. So it's a source of information to draw your information, your understanding of what those metrics of interest are. Challenges and obstacles, of course, if I start to see a lot of difference between my referent and my simulation data, how do I pinpoint the source? In particular, I'm going to talk about distributed simulation. And, I am a big believer in layering of information. I've told you, there's many opportunities to draw out your referent data, and you build information over time. But when you're talking about distributed simulation, you're piecing together these various simulations, which in many cases were not intended to ever work together. And so you really need to do that deliberately, And so I'm, gradually build up your information, because if there are problems, I need to be able to pinpoint the problem. I need to be able to re-engineer what caused the problem. If I've just put everything together, assembled all my whole federation, and turned the switch, chaos will ensue. And then how do I determine what was the source of the chaos, right? So this idea of inconsistencies and trying to identify inconsistencies is very important. And one way to address that is deliberateness of process. Of course, I talk about reference. I talk about the importance of reference. What happens if you don't have it? What if you don't have a source? If you don't have? Now, again, there are options. The reference that I showed you, the various sources, there are spectrums. So the lower end of, and I know even in the test and evaluation community, they don't look at subject matter experts as the strongest referent. But in some cases, that's all you have. Use all the information you have. So sometimes you have to think outside the box a little of where you get that information. And then, of course, the other is economic limitations. And it's not just always money, even though I put that up there. We put that up there. Sometimes it's just schedule. I can't tell you how many times I've encountered where my referent data is coming, my ability to access the referent data is 3 months, 4 months out before I have to support an IOC or some key milestone, decision milestone. There's just not enough time. It's just not feasible. I cannot get my referent data, build my data sets to run my model, because I have to match up to the reference situations, the scenarios, right? Run my scenarios, do the analysis, put all the evidence together, build my case, go to a simulation control panel meeting, go to an accreditation review panel meeting. I just don't have time. It's physically impossible. And so, that when we talk about schedules, this I can't tell you how many programs I have where I have a risk that is taken to the risk management board about the proximity of the validation, referent data availability, and the decision point, right? So that's definitely a challenge. So what can you do? How can you address this? And I need to move quickly here. Start early. Get your validation referent started. Start thinking about, again, what metrics you need, what are your opportunities, work with your testers, ensure the accreditation authorities on board, that they are aware of the reference sources you're using and they agree with them. Grow your referent over time, I've been talking about that. Maximize the extent of the coverage and define those areas of uncertainty. So I'll give you a couple examples and I'm going to turn it over to Michael here. So this is a situation, AIM-9X. This is a bit dated, but I think it is a great exemplar. And in fact, in NTSA, they won an award. This program won an award for the use of simulation, the application of simulation within its use. So AIM-9X Sidewinder, they had an issue that all testers encounter. I have limited test shots that I can perform. How do I maximize that, right? And so there was this test model construct that was applied where they worked intimately with the modelers and the testers, and so they would model the various scenarios to try to drive to those edge conditions, and then that would determine where they would do their testing. Now, of course, there are issues with that, but ultimately what they were able to do, they were able to decrease significantly the amount of test shots that they needed to build the confidence in the system performance. Also, with subject matter, so that's with your test data. Now, when you have a subject matter expert referent, I talked about by nature they're subjective. But also with all statistics, what do we want to do? We want to build our sample space. Michael's going to be talking about this in a little bit from the context of live test data. But with SMEs, you can do the same thing. You can grow your referent. You can grow the strength of the referent by increasing your data points. So instead of having a single SME doing the evaluation, you build a group of SMEs, a SME panel, and then you evaluate using potentially a survey of how they think a particular situation will play out. And then you look across the responses to see consistency. That sounds a lot like what I talked about with the meteorological models, right? That same idea. I increase my samples, and I look for consistency across my resulting statistics. And this is just another case that talks to the same thing. This is a case that Michael actually worked, where they had a joint operations feasibility tool, and they wanted to employ the same concept. They were reliant on subject matter experts, and so they developed a set of scenarios. They had 20 different subject matter experts. They elicited insights from them through the surveys, and then looked across those surveys to do some analysis and produce a stronger assessment of how the situations might operate. So with that, I think I am going to, I'm hoping I set the stage here for Michael. He's going to take it from here and talk more about the validation methods and how you would apply them.
Thank you, Simone. All right, gentlemen, don't raise any hands, but how many of you had this experience? This morning when I got dressed, I was tying a necktie for the first time in almost 2 years. I wasn't sure I'd remember how, right? How'd I do? Okay, who's ready for some mathematics, right? You know who you are, all right? We're going to have some mathematics. Now, just humor, we've got 3 or 4 more conceptual slides, but we are going to get to some mathematics. Whether that's good or bad is up to you. All right. I know this will work if I do something right.
Yeah, it is that top button. It just takes a while.
It's just a pointer. It doesn't change. All right. All right. Rigorous validation requires rigorous validation methods. Okay? And rigorous validation methods depend on a lot of things, notably the referent data. But before we get to the referent data, there are a couple other things that rigorous validation methods depend on. The model, in other words, certain types of validation methods are most appropriate for certain types of models. The resources that are available in order to execute validation. The skills of the people who will be executing validation. All those things are considerations in choosing a rigorous validation method, but those are not the subjects of this tutorial. The subject of this tutorial is rigorous validation, and in particular how the referent drives and is related to the rigorous validation method. Okay, so in this part of the tutorial, I'm going to start by making the connection between the referent that you have available and the method you should choose. And the relationship is two-way. If you have a referent, that will help you choose the method. But if the method has already been chosen, either by you or by, say, the accreditation authority, then that will tell you what referent you have to develop. So I'm going to make that connection first between the referent and the rigorous validation method. And then in the second part of my presentation, I'm going to give you 2 examples of rigorous validation. And Simone has already mentioned the 2 types of examples. The first one is going to be a point estimate, something like a mean, although I'm actually going to do variance instead, just for the change, pun intended. Then in the second example, we're going to do time series. Time series. Now, the rigorous method I'm going to use in the first case is probably familiar to any of you who've had a statistics course, but the rigorous method in the second case is perhaps unfamiliar. Simone and I were talking before we started how strange it seems that no one has really gotten into time series analysis and validation, at least not to the extent that we would have expected. Oh, that's still only okay. I'll learn sooner or later. Before we get to the mathematics, though, let's consider the possible relationships between the referent data you have available and the intended uses of the model. In both cases, I'm representing the referent data and the intended uses of the model abstractly in terms of these geometric extents, or shapes. These shapes within a 2-dimensional coordinate system, and so that implies, for the sake of simplicity, I've reduced the number of variables in the referent data and the number of variables in the intended uses to 2, but you know as well as I do that it's normally a lot more than 2. So it'll fit on a PowerPoint slide. We have 2 variables for our referent data and 2 variables for our intended uses. And so the intended use data represents the range of inputs that you might put into the model, and the referent data represents the range of inputs for which you've acquired your referent data. So in this diagram, the green ovals represent the data range of the referent, and the blue rectangles represent the data range of the intended uses. And ideally, we're always in this non-existent world. Okay. The best of all possible worlds. Yes, that's what I want to say. The best of all possible worlds. The intended uses of the model are completely within the range of the referent data. Wouldn't that be great if it always worked out that way? So if we could validate the model completely for all the possible intended uses, then Simone and I would quickly have to switch to another field. But more often, we're in one of these other 3 fields, and if we're in the upper right situation where the intended uses are larger than the referent data, but we have plenty of overlap between the referent data, or if the intended uses and the referent data aren't really one within the other, but there's still some overlap, then careful rigorous validation, perhaps supplemented by subject matter expert-based methods, Combinations of validation methods are often good. So careful validation, combinations of validation methods can help us deal with the upper right and the lower left. In the lower right, there's zero overlap. And not only is that contradictory to Dr. Gilmore's instructions on one of the previous slides, but it makes me very, very nervous when people want me to validate a model. People ask me to validate a model, and their referent data has no overlap whatsoever to their intended uses. Right, Simone? So this diagram illustrates in a simplified way how the sources of referent data that Simone talked about earlier relate to the forms of referent information that you might have. Different sources will provide data, referent data, in different forms. And so we have in the left column those different sources that were on Simone's slide. And in the center column, we have different forms of data: single observations, many observations, paired observations, and so on. And the rightmost column then tells you a selection. Obviously, I can't fit them all on the slide. You saw Simone's earlier slide with 85 verification and validation methods on it, but a selection of possible validation methods that we would categorize as rigorous. And what they all have in common is some sort of statistical or mathematical element. So for the time being, we'll just treat rigorous as a synonym for mathematical, or quantitative, if you like. So in row 1, we have only a single observation or a few observations of the simulant. So you can use confidence intervals or multivariate confidence intervals in these situations if you can run the model more than once. I'll give you an example of that later. Sometimes empirical data or theoretical data can give you many observations, in which case you can use the old standbys of hypothesis tests for means, variance, proportions, and distributions. And that's, in fact, going to be my first mathematical example. If you have paired observations, which is ideal, right? You have the model has been executed and the simulant has been observed under exactly the same input conditions, and ideally the model's execution, the model's output should replicate what happened with the simulant. Then you can use regression analysis, which is extremely powerful, and in my experience, extremely convincing to the accreditation authority. If you're forced to fall back on subject matter expert knowledge, and all you have are the subject matter expert's expectations and experience, don't give up. Don't throw up your hands and say, look, I followed all the steps properly, all right? You can still use the structured face validation that Simone was speaking about just before she handed off to me, where you don't just throw the subject matter experts in front of the computer and say, does it look right to you? No, you have carefully constructed scenarios, you have questionnaires, you have a designed experiment in order to elicit true expertise from the subject matter experts. And my students and I have often fallen back is not the right word. We've often supplemented quantitative rigorous validation with a Turing test, where we've asked subject matter experts to tell us if they can tell the difference between model output and real-world results. So forms of the Turing test. So let's start with hypothesis testing. This is ideally a review for everyone who's had a statistics test. And hypothesis testing, as the previous slide said, can be applied when you have multiple simulant observations available, and you use some form of hypothesis test to tell us whether the simulant observations are consistent with the model results. Not identical, but statistically consistent, statistically comparable. And there are lots of different hypothesis tests that compare things like means, variances, and distributions of the model results and the simulant results. And ultimately, if the hypothesis test does not reject the assumption of validity, then the model is considered valid. And I'll have some more to say about that in a minute. Now, if you don't remember your statistics that well, shame on you. If you don't remember your statistics that well, what statistical hypothesis tests do is they make inferences about a population based on samples drawn from the population. Obviously, we could perfectly know the mean height of everyone who's attending ITSEC if we measured the height of everyone who's attending ITSEC. But if instead I just measured the height of the people in the room, I could still make a reasonably good estimate of the mean height of people who are attending ITSEC. So that's what statistical hypothesis tests are all about. Now, what we're going to do next is actually compare variances rather than means, because everybody always does means, and that's just routine now. Let's see if there's something else I want to say here. Oh, yes. In validation, when hypothesis testing is used, they're conventionally formulated where the null hypothesis is that, let's talk about means for the moment. With the null hypothesis, H sub 0 is that the mean of the model's results is equal to the mean of the simulant observations. as recorded in the referent. The mean of the model is the same as the mean of the simulant. And that sounds a little bit like cheating to me because we're assuming the model is valid and looking for convincing statistical evidence that it's not valid. But the advantage of that formulation, and it is the conventional formulation, is that it makes the type 1 error and type 2 error of the statistical hypothesis test, the statistical type 1 and type 2 errors, consistent with the validation type 1 and type 2 errors that Simone showed us earlier. Okay. So here's your example of a hypothesis test. If I can make the slide advance, how many times will it take me to learn that this doesn't work? All right, so we're going to do a hypothesis test that involves the SCUD. We're going to compare the variances instead of the means, like I said, just for variety. Scud missiles, as you probably know, are single-stage liquid-fuel tactical ballistic missiles. Aside from the World War II era V2, the Scud missile has the largest number of combat launches, so it's a widely used missile and it's been widely deployed. And we're going to validate a model of the missile's trajectory. It calculates the missile's trajectory from launch to impact based on certain initial conditions, such as launch angle, launch azimuth, wind speed, motor performance, and so on. The model is a physics-based 6-degree of freedom model. It's a deterministic model. In other words, same initial conditions give you the same answer. So what changes from trial to trial are the initial conditions. It's written in MATLAB Simulink, and we're setting the initial conditions, well, not we, but the study I'm reporting is setting the initial conditions using Monte Carlo methods. And before I go any further and start showing you missile impact data, just in case anyone is a little bit nervous that I'm going to say something classified about missile accuracy, let me say that the study I'm reporting was performed by scientists from the People's Republic of China, and the data I'm reporting was published in the open literature, so set your concerns aside. Okay. Yeah. Okay. So these are the model results that you're looking at least mostly what you're looking at are model results. There were 1,600 trials, 800 trials at the 60-kilometer range, and 800 trials at the 100-kilometer range. And each of the model's results are shown by the green circles. Yes, there are 800 circles there piled on top of each other. And there are 800 more circles piled on top of each other. You can immediately see with your highly evolved visual cortex that at 100 kilometers the missile impact points are dispersed a lot more, as you would expect. Now, what are the blue dots? Well, there are also 6 live trials of real Scud missiles. There are 6 live trials of real Scud missiles. So we have 1, 2, 3, 4, 5, 6 of those each. And the validation question is our physics-based 6-degree of freedom MATLAB Simulink model performing the same way that the actual missiles did? And we could validate the mean impact point, but instead we're going to do the variance, which is the dispersion, the measure of how far the impact points are off from the aiming point, which of course is the red plus sign at the center. And we're going to do actually 2 hypothesis tests for each of these 2 ranges for a total of 4 hypothesis tests. See how I did that? 4 hypothesis tests. The error in the x direction, which is range, and the error in the y direction, which is across range, or deflection, or azimuth. Choose your favorite term there. And what we're going to do is compare the variance, the dispersion, for each of the 2 ranges for each of the 2 measures. And you can see the raw data here, the raw data from the 800 simulation runs is right here, and the raw data from the 6 live trials. This is our referent right here. This is the raw data from, 800, I think I said 600, 800 simulation runs and 6 live trials. All right, so at this point, if we weren't doing rigorous validation, if we were doing what I'll call using the that looks about right method, the TALAR method, we'd look at those numbers and say, that looks about right, okay? But we're not going to do that. This is rigorous validation. All right, so the F-test is what we're going to use to compare the variances. You all remember the F-test, of course, but just in case, you obtain samples and calculate the sample statistics. And the modern version of the F-test, this is not the way I learned it when I was an undergraduate, but this is the way we do it now. We're going to set the notation so that S sub 1 is greater than S sub 2. S without the exponent is the standard deviation. S squared is the variance, and S refers to the sample. We don't have the population data, we have the sample. We select the level of significance. That's the probability of making a type 1 error under the assumption. Let's see, let me say this correctly. A is the level of significance, the probability of incorrectly rejecting H sub 0 under the assumption that H sub 0 is true. And that's a type 1 error in statistics, and it's also a type 1 error in validation under the assumption that I described earlier, the formulation that I described earlier, where the null hypothesis is that the model is valid. And we formulate our null hypotheses. We calculate the test statistic. It doesn't get much easier than this formula for calculating the test statistic. Even my daughter can do that. Given the test statistic F, we find the p-value. Now, when I learned statistics as an undergraduate, we didn't do p-values, we did critical regions, but now they do p-values. And the p-value, for those of you who aren't familiar with it, is the probability of the sample producing a test statistic value at least as extreme as the one you got under the assumption that the null hypothesis is true. And if the probability is low, that means the result implies that the probability of the null hypothesis as being true is low, and if the p-value is low enough, then you reject the null hypothesis. So if the p-value is less than or equal to alpha, reject the null hypothesis. That's how you do it. Okay, that's the end of your review of statistics for the day. What you see here are the 4 hypothesis tests, one per column. As it turns out, in all 4 cases, the variance, actually these are the standard deviations. The standard deviations for the simulant are greater than the model. That's just a coincidence. It doesn't have to be that way, and it isn't always that way. It's just worked out that way. In this particular data, the variance for the simulant was greater than that for the model. Now the question is this variance large enough, is the difference between these variances large enough for us to reject the null hypothesis that the model is valid? These are the F statistics calculated according to the formula. These are the degrees of freedom, 800 model trials -1, 6 live trials -1. And these are the resulting p-values calculated by looking up in the back cover of your statistics book or using any online calculator. All 4 of these p-values are kind of low. They're all in the 0.3 range, but they're nowhere near as low as alpha 0.05. Nowhere near as low as alpha is 0.05. So what we have here is not enough evidence to reject the null hypothesis that the model is valid for variance both in the x direction and in the y direction. Okay? I went through that pretty quickly because time is limited here. What I'm hoping is that this is all coming back to you. It's all resurfacing from the depths of your cerebellum as I explain it. And now you know what validation can be done in a rigorous way for this kind of situation. Let's turn to the second example, which I'll go through a little more slowly. So for the second example of rigorous validation, we're going to consider a different type of data, time series data. Instead of just looking at a single point value, say the variance in the x direction, we're going to look at time series data. Now, a time series is a sequence of observations of the same variable. You measure the same thing over and over again, typically at evenly spaced time intervals. That's what we mean by a time series. All right? Now, suppose we have a model of attrition combat. I'm actually going to spend a few minutes telling you about the model of attrition combat that I'm using for this example, but not yet. I want to motivate your interest in that model. So suppose we have a model of attrition combat, and it reports, among other things, it reports red casualties at each moment in time, red casualties at each moment in time. And suppose we're going to use this model to recreate an actual battle, which we will call one trial of the simulant. I know that hides a lot of the tragedy of an actual battle. I understand that. But we're still going to call the actual battle one trial of the simulant. And we have 15 trials of this attrition model running a replication of the same battle. Now, if we did validation the way it's often done, we'd pick some arbitrary time, say 50 hours after the battle started. Some historian has told us that's when the battle ended. So we'd pick 50 hours after the battle started, and we'd observe red casualties in the actual battle at 50 hours, and we'd observe red casualties at 50 hours in the 15 trials of the model, and we compare them, and that's what you see right here. If you look closely, you can see the green dot right there. That's the one trial of the actual battle, and you can see the 15 pinkish dots around it. Those are 15 trials of the model, and the way we often validate is we'd say, look, that value is right in the middle of the simulant value is right in the middle of the model values, I'd say that model's valid, right? And it can be very misleading to validate a model at a single point in time. If the model produces output over time, and I've emphasized how misleading that can be by deliberately leaving all this blank, just to tell you, yes, something is missing. In fact, here's what's missing. This green line is the time series for the actual battle, our one trial of the Simulant, and these pink curves are the model trials. I don't need to tell you that there's something wrong between that model with respect to that Simulant, and the fact that they happen to agree at 50 hours is probably just a coincidence. You got lucky when you chose the 50 hours. All right, so what we really want to do is validate along the entire time series, not just at 50 hours. I was surprised, and I can't speak for Simone, but I think she was surprised that hasn't been as much attention given to this aspect of validation as we would have thought over time. And so we're going to take a quick look at it over the next few minutes, until Lee cuts me off. Before we get there, though, let me just talk about the model a little bit so you know what's going on. I'll go through this quickly. In order to support this example, I developed a attrition combat model. It's force-on-force attrition, direct fire only, no area fire, nothing fancy, just direct fire. Battle continues until one side breaks, where one or the other of the forces has taken enough casualties that they consider survival more important than mission success. And the input parameters are strength, lethality, break point. And the question is, who wins the battle? And this kind of fighting actually did occur in the opening months of World War I, as suggested by the photograph, before the trench lines were built. This model, if you're interested, goes by the technical name Markov chain Lanchester attrition. It's got these variables: blue strength, red strength, blue lethality. Blue lethality is red casualties per blue shooter per time unit, and red lethality is blue casualties per blue shooter per time unit. And the casualty rates are the lethality. The red lethality times the number of red shooters, and the blue lethality times the number of blue shooters. And we're using lambda for an important reason. If you remember your probability distributions, you can guess where I'm going. We're using lambda and calling them the casualty rates. These are the assumptions of and abstractions of this model: direct fire only, no maneuver, all shooters have the same lethality. Lethality does not change. Multiple shooters can engage a single target. You can argue with any of these assumptions, but this is an example. So if you remember your probability distributions, the exponential distribution is typically used to model random independent events. So given the lethality rates that we calculated on the previous slide, we're going to say that blue casualties are exponentially distributed, and we're going to use the blue casualty rate to calculate the inter-casualty times. It would be inter-arrival times if you're doing discrete event simulation. We're going to call them inter-casualty times. And the time between red casualties is likewise exponentially distributed with the red casualty rate. And we're going to use it to calculate inter-casualty time for the blues. So the way the model logic works is stochastically generate the times of the first blue and red casualty using the casualty rate. Look at the two of them, decide which one came earlier, advance time to that earlier casualty time, decrement strength of the side that lost, that suffered the casualty, then generate the next casualty time for the decremented side, and then repeat that. Continue to advance time to the earlier casualty time, decrement the strength, and generate the next casualty time. All right, so I ran that model 30 times. You can see 30 time series. The model actually outputs 4 time series per trial, and you can see all 30 of the red strength time series here, all 30 of the red casualty time series here, all 30 of the blue strength time series here, and all 30 of the blue casualties time series. I want to say that the casualties are cumulative. In other words, we're not saying that there were 3 casualties in this time unit and there were 0 casualties in the next and there were 2 casualties and the one after that. These are cumulative, so the time series are telling you total casualties suffered from the beginning until a given time. At time t, it's the sum of all the casualties from time 0 to time t. So consequently, these time series are monotonically non-decreasing. For the rest of this example, we're going to focus entirely on red casualties, just because We don't have all afternoon, and you want to go look at the exhibits, but we are going to focus on red casualties, and a similar analysis could apply to the other 3 output variables, red casualties. So how are we going to validate time series? Well, it depends. As always, it depends. And to tie back to what Simone was telling you, it ties back to what you have as your referent. Ties back to what you have as your referent. And so I've categorized the situation into 3 possibilities here. You have one trial of the simulant and you have one run of the model. You have one trial of the simulant and you have multiple runs of the model. This is probably most common. Or you have multiple trials of the simulant and you have multiple trials of the model, and there are slight differences in the method that I'm about to explain to you for each of these situations. I will say that in all 3 of these methods, we're going to use confidence intervals, nice and simple, near and dear to my heart. There are more advanced methods, which I will briefly mention at the end of my portion of the presentation, but we're going to be talking about confidence intervals for the next few minutes. Now, where do the confidence intervals come from? The answer is different depending on how much data you've got. You can't calculate confidence intervals from your imagination. You have to have data to calculate confidence intervals, and so I guess if you're an SME, you can do it from your imagination. But anyway, we're going to calculate the confidence intervals from what we've got, and the more we've got, the better, well, not better, but the different the confidence intervals are going to be. Now, one of the things that we're going to have to deal with is in all 3 situations, we're going to be setting up interval bounds. How we set the bounds depends on the referent. Well, we're going to be setting up bounds. I'll explain this as we go through each situation. But in all 3 situations, once we've set the bounds, we're going to see how often, that is to say, how many time steps is the model out of bounds. We're going to count how many time steps the model is out of bounds. So naturally, that raises the question. And if I wasn't talking so fast, you'd ask me the question, how do you know how many times out of bounds is too many? Okay? And the answer is we're going to rely on the SME. At least for today, we're going to rely on the SME. Actually, if any of you know a better way to say how many times out of bounds is too many, I want to hear from you, please. But for now, for today, we're going to say we're going to rely on the SME who's going to set an out of bounds limit. Okay, let's see how it works. So I had planned to discuss how to calculate confidence intervals, but I see I'm running short of time, so I'm just going to assume you all know how to calculate confidence intervals. And if you don't know how to calculate confidence intervals, go to any of these sources, and you'll see a nice tutorial on how to do it. Okay. So this is method A. 1-to-1 up here means we have one trial of the simulant and one run of the model. All right. Because a proper statistical confidence interval cannot be calculated in a meaningful way from a single data value, okay, you knew that, we're instead going to rely on the subject matter expert in this situation a little more than we will in the other 2 situations. So we're going to say, subject matter expert, tell us the value of epsilon, and epsilon is going to be the half width of our confidence interval. We're going to add epsilon to the simulant mean, and we're going to subtract epsilon from the simulant mean at each time step, and that's going to give us a pseudo confidence interval. And that's what you see in this slide. The green, solid green line is the simulant mean. The dashed green lines are the simulant mean plus epsilon and minus epsilon. The green shading just helps us see the confidence intervals, pseudo-confidence intervals. Of course, there's one confidence interval at each time step, and I've just shown them as a continuous band, but there's one at each time step. The purple curve is the model mean that was calculated. Remember, this is one trial of each, so we have one model run, and that's actually, we'll call that the model mean. And the question is, how many times is the purple curve outside the green band? How many times is the model mean outside the confidence interval? And if you look at the left plot, it's not that easy to see that. Right? Again, if you're using the Talar method, if you remember anything from this tutorial, remember the Talar method. If you were using the Talar method, you'd say that looks about right, but in fact, it really isn't that right, because we can revisualize it over here. This is the same data, but I've changed the vertical, the y-axis, so that instead of being red casualties in both cases, this is the model mean minus the simulant mean. The model mean minus the simulant mean. So perfect agreement between the simulant and the model is this 0 line, this horizontal 0 line. You can see the upper and lower bounds of the confidence intervals simply become horizontal lines as well. And this is the model mean minus the simuland mean. All right? And you can see sometimes it's within the confidence interval, and sometimes it's not within the confidence interval. We're going to focus our attention between times 0 and 50. And my little plot here tells me that it was out of bounds a total of 18 times. You can see some of them easily right there. But there were a total of 18 time steps out of the 50, 18 out of 50, where the value was out of bounds, according to the SME set bound. And 18 is greater than the SME set limit of 10%, which is 5 time steps. Of course, 10% of 50 is 5. 18 is greater than 5. And so we're going to say that the results here suggest the model is not valid, at least for red casualties. We're only validating red casualties here. Okay? Now, preferably, you never have to work in this situation. This is probably the most common situation. You have one run of the simulant, but you can run the model as often as you like. For the sake of making the plot somewhat legible, I stuck to 15. But if I was doing this in practice, I'd do at least 30. The something called the central limit theorem makes the statistics a lot more reliable around a sample size of 30. But anyway, I did 15 for visualization purposes. So what we're looking at here, once again, the SME is going to set the out-of-bounds limit to 10% or 5 time steps. The green line is the model mean. The light purplish lines are the individual 15 trials, and then the purple shading and the dark purple line. Let me start that one again. The dark purple line isn't an individual model run. It's the mean of the model runs, the mean of the model runs. And the light purple shading is the confidence interval for the model runs. We calculated a 95% confidence interval at each time step based on the 15 time step values at that time step, to get a 95% confidence interval. Now, once again, the question is, how often is this model mean outside of, the simuland mean? How often is the green simuland mean outside the model confidence interval? Does that exceed the subject matter expert's limit? And again, it's hard to tell in this plot, so again, I've changed the vertical axis, same data, I've changed the vertical axis. So again, perfect agreement is the horizontal line. This purple curve is the model mean minus the simuland mean. And these are the points where the simuland mean is outside of the model's confidence interval. The simuland's mean is outside of the model's confidence interval. There are 10 such time steps out of the 50. That exceeds the SME set limit of 5 time steps. And so again, this data suggests that the model is not valid for red casualties. This says nothing about blue casualties, blue strength, anything like that. All right, in the third method, we have multiple runs of the simuland. I hope it's not multiple runs of the same battle. That would be horrible. Multiple runs of the model in order to compare. Again, to keep the plot somewhat legible, I restricted it to 15 each. Again, our trusty subject matter expert has set the out-of-bounds limit at 10% of the time steps, 5 time steps. I've done 15 trials and calculated a 95% confidence interval for each time step for the simuland, and 15 trials and calculated a 95% time step for each time step for the model. And you can see the light green lines are the the simuland trials. The dark green line is the simuland mean. The light purple lines are the model trials, and the dark purple line are the model mean. And then you can see the 2 confidence intervals, because now we have enough data to calculate a confidence interval for each. The 2 confidence intervals are the 2 shaded bands. And as before in the first 2 cases, perhaps even more so, it's hard to tell what's right and what's wrong when you look at it this way. But when you replot the data so that the y-axis is model minus simuland, and perfect agreement is the horizontal 0 line. Now the question is, how often is the model mean outside the simuland's confidence interval? Turns out there's only one time step where that occurs, only one time step. So we conclude in this case that the model is arguably valid for red casualties. All right, confidence intervals are about the simplest statistical tool available to us, and they're often used for that purpose, not just by me, but by lots of other people use confidence intervals. It's easy to find the confidence intervals being used for validation purposes. But there are other more sophisticated methods, more advanced methods that might be useful in other situations. I happen to be particularly interested in Granger causality. Anyone heard of Granger causality? Yeah, I hadn't heard of it either until I started digging into this. Granger causality is not new, but it's a statistical method for assessing how well one time series predicts another time series. Right? Does that sound interesting? I mean, we were talking about a model time series and a simulant time series. How well does one time series predict another? Now, as Granger formulated it, there was a lag between one time series and the other, so we might be trying to predict how well does sales of Coca-Cola predict rise and fall in the S&P 500. That's what I guess he had in mind when he thought of this, but I think we can apply it to Simulant and Model. And so I'm digging into that, not right at this moment, but in my spare time. All of these references, by the way, are in the are going to be on a slide, but I assume they're going to be in whatever form these presentations are made available. So perhaps when I'm done, Lee will tell you how to access these presentations. All right, so we're into the conclusions. Do you want to do the conclusions, Simone, or should I go ahead? All right. All right, the main point, or one of the main points of this presentation, is that the quality and quantity of the referent affects the validation rigor. You can't apply these statistical methods that I've given you a glimpse of unless you have the right data to support them. Okay? So rigorous validation is possible, but you have to have the effective referent, which means the right data and enough data to support the methods you want to use. And as I said, it goes two ways. If your referent is fixed, then you choose a rigorous method that is within what that data will support. And if you must use a particular method, then that tells you what referent data you have to acquire. Simone emphasizes this all the time. You should start early in the simulation life cycle. Don't wait until 3 weeks before the model validation is due to be completed before you try to acquire referent data. And a corollary to the fact that validation methods depend on referent data, if you get a better referent, you have more validation methods available to you. And the truth is, these statistical methods, once you know how to do them, don't take particularly long to calculate, nor are they particularly hard to implement. So if you get more referent data, you can use multiple statistical methods. I'm a big fan of using multi-method validation. Now, here's a caveat, a cautionary tale. Almost all statistical methods, when you pick up the statistical book and you look them up and you're in a hurry just to get to the formula to calculate the test statistic, when you overlook the first few paragraphs where it says this is assumed and this is assumed and this is assumed, and if these assumptions aren't met, the statistical test is meaningless. All right? For example, the F test that I used before depends on the assumption of normality of the populations that the data is drawn from. And if you do an F test on populations that aren't normal, you get a meaningless answer. You'll get an answer, but it's meaningless. So if you're using statistical validation methods, you have to assume that the assumptions are met. And finally, I gave you a glimpse, a little look at how to validate a model using time series data. And perhaps the more important point than the specific methods, although the methods are good, the more important point is recognize when you have time series data. Don't just validate your attrition model at time 50. Validate your attrition model over the entire time that the model is being run. Recognize when you have time series data and apply an appropriate method. And as I showed you, that you can use confidence interval methods that are relatively simple, and then there are more advanced methods available for those of you who are so inclined. These are the references that Simone and I included in our slides, and that will be available to you if you want more information. If you'd like to contact Simone or I, here is our contact information. I'm sure I can't speak for Simone, but I'm confident, pun intended, that she'd be happy to talk to you, and I certainly will. Yes. Okay. Lee, do we have time for questions? Right. Does anyone have a question for Simone or I?
So I will say, we have been really emphasizing, one of the programs I'm working on, this idea of time series data is very important. And so
go to the show floor.